Guys, today we're going to kind of review what our parent functions are, and we're also going to talk about something involving the symmetry of a graph. So your central question today is, how can I tell if a function is even or odd? So the first thing we need to do is define what an even and odd function are, and then we can apply it to those parent functions that you've been talking about since Algebra 1, Algebra 2. So the first thing that we need to know is what the definition of an even function is. So the mathematical definition of an even function, it says if f of negative x is equal to the beginning function f of x, then this entire function is considered even. So that seems kind of weird. That's kind of like the algebraic way to think of it. Now looking at the graph is where it becomes it's a lot more intuitive to figure out if something is even or odd. So on the graph of an even function is always going to be symmetric about the y-axis. So if both sides of the y-axis are mirror images of one another, just like the letter capital A, that means that the function is going to be even. So if you had the point AB on the graph, the other point that's going to be on the graph is also negative AB. And we're going to look at an example of that in a second. So again, if you look at a picture of a graph and it's symmetric, you can fold it over the y-axis, that means that your function is even. So an example of an even function is our favorite f of x equals x squared, that quadratic parent function. So if I wanted to make my graph of that, and let's just say I had no idea what this graph was, I can always plug in points. So if I plugged in x is 0, then 0 squared would get me 0. If I plug in f of x, or I plug in x is 1, then I would have 1 squared is 1. If I plug in 2 squared is 4, and so on and so forth. So I could make that picture. Now, the thing about an even function, and they're telling you this is an even function, if I draw this half of the graph, the other half of the graph, I did not hit that point, but the other half of the graph needs to be reflected or mirrored over the y-axis. So I really don't even need to plot those negative values because I would know that I would need to go through those same points on the other side. And while mine is not perfectly symmetrical, you kind of get the point. If I fold my graph over the y-axis, it would be the same on either side. So knowing that, the point 2, 4, we know that was a point. We plotted it. 2 squared is in fact 4. And the other point that's going to happen using this little thing would help me. But I would know that if I go over to negative 2, I would also have that positive value for b. So negative 2, 4 is also on the graph. So that means since this is even, if I plug in that negative value, or I just take this value and I make it negative for x, then I'm going to get whatever I originally got had I plugged in the positive value. So again, an even function, I can fold it over the y-axis. Let's talk about an odd function. So again, we're going to start with that mathematical definition. An odd function, if f of negative x equals negative f of x. So again, that negative sign is now flipping and going outside of your function. Then f of x is an odd function. Okay, so let's talk about what that looks like. That's still kind of weird if you look at it just like that. So the graph of an odd function isn't symmetric about the y-axis. It's going to be symmetric about the origin. Okay, so if it's symmetric about the origin, what's going to happen is whatever you had in quadrant 1 is going to end up the same thing in quadrant 3. So we call that rotational symmetry, but basically the graph is going to rotate around 0, 0, around that origin. So if you also want to write down this is rotational symmetry, sometimes they like to refer to it as rotational. Oh, I hate spelling this word. Okay, I got it. So we're rotational symmetry. So we're again going to look at a picture, but if it doesn't reflect exactly over y, then it's not even. And if it goes in like kind of a rotational, like I can turn it around and it'll become, that's an odd function. Okay, so what that means is if AB is on the graph, then the point negative A and negative B are on the graph, which is kind of what we set up here. If I make my x negative, then my y also has to become negative. Okay. So an example of an odd function is f of x equals 3x. This is going to be a linear function. It's not the parent function, but it's a linear function, and it'll show us what this is going to end up looking like. So let's graph it. Again, if I was, you know, so lost and I didn't remember that this was just a linear function with a slope of 3, I can always plug in points. If I plug in 0, and I'm going to get 0, 3 times 0 is 0. If I plug in 1, I'm going to get 3 times 1 is 3. I'm trying to make sure I'm on my dots, okay? And then if I plug in 2, I would get 3 times 2 is 6. So 3, what did I just plotted that wrong, didn't I? Life, I plotted 3, 3. It's 1, 3, and then 2, 6. I got this. And then if I wanted to go backwards, again, I could plug in negative numbers and see if what happens there. But if I use this definition up here, I know that if I make my x negative, then my y becomes the same number, just negative. So if I plug negative 1 in, I should be getting negative 3. And if I plug in negative 2, I should be getting negative 6. I'm going to go ahead and make this look nice. Well, I tried. But that would be the graph of this line. And if you look at this, you can see whatever was in quadrant 1 is now over here in quadrant 3. The graph rotates around the origin. So this is an odd function. So similarly, the points 2, 6, and we just said the point negative 2 should go to negative 6, which then means that if I plug in a negative value for x, I get that same value for y, just negative. Okay, so again, even functions are going to be just fold over the y-axis. Odd functions, they're going to end up rotating around. They have that rotational symmetry, and we're going to look at some more examples of odd functions. They're kind of, well, odd. Haha. Okay, so we're going to look at these parent functions. These are all parent functions that you probably know. Now we're just going to make sure we know some of the attributes to them, put some, words, some notation into things that you probably already know. So this first parent function, y equals x, very, very nice. That was the first one you started with in Algebra 1. It's linear. And if I look at this, I can see that this function has rotated around the origin. It has the same in the first quadrant as it does in the third quadrant, which makes this function odd. So the parent function for a linear parent function is odd. Okay. To remember our domain and range, remember domain goes from left to right. So for this one, since it has arrows on the end, we have all real numbers for my domain. And similarly, range goes from bottom to top. So from this bottom point up to this top point, again, there's 2 arrows. So they're going to be going on forever. Now, some notation that you may not have seen, when we talk about end behavior, we're talking about what is going on at the very, very end of the graph. Like if I could keep going forever and ever and ever to infinity or negative infinity, what does the graph look like? So as x goes from negative infinity, so as it's going to negative infinity, what is y going to do? So as I'm going, making my graph smaller and smaller in the x direction, I see that I have this arrow down here that's going down. My y is also going to get more and more negative. So as x goes to negative infinity, y is also going to go to negative infinity. Okay, it's just asking you what's happening at the ends. So same deal here, as x gets bigger and bigger and bigger, y is also getting bigger and bigger and bigger. And then how we note that is just say it goes to infinity. Okay, we're going to look at the next one to the right. I don't know my directions today. So this function right here, when we put those bars around the outside and it looks like that V shape, that's the absolute value parent function. We don't do a lot with this. It's a very useful tool to have. But looking at it, if I take my graph, I can fold it over that y-axis and it's the same on both sides. So this would be an example of an even function. Okay, so again, this guy rotated around the origin. This one went ahead and did the just flip-flop, just make sure same in quadrant 1, quadrant 2, basically. So my domain, again, I see that it's going all real numbers, or negative infinity to infinity. Now here the range, it only starts at that bottom point of 0, and we can include 0, so we put that square bracket. That square bracket kind of looks like an equal sign. Okay, looking at the end behavior, as x gets more and more negative, my y is going up. So I would say that as x goes from negative infinity, y is going to go to negative infinity, or sorry, positive infinity also. I'm just getting my infinities confused. So as x goes to negative infinity, y is going up, it's going to positive infinity. Okay, same deal for making it bigger. As it gets bigger and bigger and bigger, y is also getting bigger and bigger and bigger. So my end behavior, they're both going to positive infinity. Okay, next one, my friend quadratic. We already kind of talked about this guy. Again, you can fold this over the y-axis, so he is even. My domain is, again, all real numbers. You're going to notice a lot of my parent functions are all real numbers, but this one is just like the absolute value. It starts down there at 0, and I could equal to 0 because 0 squared is 0. The end behavior, again, is almost exactly the same as the as the absolute value. As your x is getting smaller, your y is getting bigger. You go, and as your x is getting bigger, so is your y. Okay, let's try a different one. This guy right here, this is the square root function. Now looking at this, I can't fold it over the y-axis and get the same picture. That would have to look something like that, which we don't have that at all. And I also don't have that rotational, because if I rotate, whatever's in quadrant 1 is not in quadrant 3. So this function is neither even or odd, which is okay. It can be neither. The domain of it, again, where we start from left to right, so it goes from 0 until infinity. Now I can equal 0. I can take the square root of 0. It's 0. So this point is good. I can put the square bracket around it. Same deal with the range. Starts at 0, goes up to infinity. Just gets to infinity kind of slow. Now here, I only have one type of end behavior because my graph isn't going to negative infinity. So as it goes to positive infinity, my y is also going up. So I would say my graph is going to positive infinity. Okay? If at any point you want to pause me and like try these by yourself and then see if you got it, by all means. So we have y equals x cubed. This is the cube function, cubic. And again, if I look at it, whatever I had in quadrant 1 is just reflected in quadrant 3. So this one's going to be another example of an odd function. Again, the domain is all real numbers, and so is the range. So my end behavior, again, if I look on the left part of the graph, it's just going down. So as x goes to negative infinity, y is also going down. And as x goes to positive infinity, y is going up. Its inverse, its friend, the cube root function, is similarly also going to be an odd function. Looking at the picture, I can see it rotates itself around the origin. The domain is, again, all real numbers because, you know, the inverse just flip-flops its domain and range. And then the range. Oh, that was the worst infinity I've ever drawn. Okay, nice try, self. And then the weird thing about this, the end behavior is actually exactly the same as the cube function. Because right here, I look, it's still going down. It's going to go down slower, but it's still going to get to negative infinity. Could I let my graph go on forever and ever and ever? Okay, if I take the cube root of some sort of large number, it's still going to be a pretty large number. And so same deal going to positive infinity. We're getting there. We're almost done. So I look here. This guy's an exponential function. If you have x in the exponent, it's exponential. And again, this one doesn't have any sort of symmetry. So I would just say it's neither. So if I'm looking at this, I can't fold it over. I can't rotate it around the origin. So it's neither. Now this one, the domain, is going, we see it's going up to positive infinity. We're not sure what's going up down here. So if I look, this domain is going to actually start at 0, but I can't equal to 0 because I have something called that horizontal asymptote. I'm going to try to spell it. So that horizontal asymptote is going to stop me from being able to actually hit that point. So I'm going to put that parenthesis around it instead. The range is going to do the same. Oh, I messed that up. I did my range first. Domain is good. I can plug in anything into that. I got so excited about that horizontal asymptote. Domain, I can have that. There's an arrow down there. It's the range that has that problem. So when I look at it, we're just going to put the parenthesis around. Okay, the end behavior then, as I'm getting closer and closer to negative infinity, my y is going to end up going to 0. That's what it's getting closer and closer to. Whereas it's getting, if I'm going up, then that one's going to end up being positive infinity. Okay, this one's a logarithmic function. And again, this one is neither. Because I can't fold it over, I can't, the first quadrant's not the same as the third quadrant. And again, this one is actually the inverse of the exponential. So my domain and range are just going to end up flip-flopping. So my domain goes from 0, again, don't include it, and then my range is actually still negative infinity to infinity. Now the end behavior, this is something we're going to talk about later. It's okay, but it's going to be going, again, we're going to kind of flip-flop it. As x goes to 0, y goes to negative infinity. And as x goes to infinity, y goes to infinity. We're going to finish the other ones in class. Have a good night.